So, so today we will be discussing about photonic quantum computers and optical quantum computers. So, yeah, first we should know some abstracts and some of the things that are there in computer first. So, what is computer? So, computer is a simple logic device which consists of a two-bit logic that is known as the logic gates, right? And these logic gates constitute to make circuits, and these circuits constitute to make the communication systems. So, basically, we can say a computer. Basically, a computer follows the laws of Newtonian physics or mechanics. But due to advancements in technology, the size is shrinking day by day, and maintaining these laws of physics are getting tougher. So, quantum physics or mechanics are introduced to maintain the next generation computer or computation technologies. Now, sorry. Quantum mechanics is a fundamental theory in physics where that provides the description of physical properties of nature at the scale of atom and subatomic particles. This quantum mechanics is used to compute data, which is known as the quantum computing. And unlike normal computers that we use in our day-to-day life, quantum computers are different in terms of size, speed, storage, and many other aspects. So quantum computing is the use of quantum phenomena like superposition and entanglement to perform computation of data. And photonic computing and quantum computing are merged together to create photonic quantum computers. Now, let's give you a brief introduction how it all started and all. Then we'll move with the theory and other aspects. So, when computer generation began in the late 1950s or 40s, when the digital machines using transistors became commercially available. In this traditional approach to computation, information is stored in bits that are represented as 0, which is off, or 1, which is on. So advancements in the computing technologies introduced optical or photonic computing. Now, optical or photonic computing uses photons produced by lasers or diodes for computation. For decades, photons have promised to allow higher bandwidth than the electrons used in conventional or classical computers. So just like classical and optical or photonic computers, quantum computers is also introduced. And unlike classical and optical computers, quantum computers uses ones and zeros as bits and also uses a third bit that allows them to represent 1 or 0 at the same time. So there are 3 bits in a quantum computer, 1, 0, and another bit is there which may represent 1 or 0 individually or at the same time. Now it may the question that how small for a transistor can be. So first we'll see that, then we'll move on. So here we can see there's a picture which shows the evolution of microprocessor manufacturing processes. So first was the Intel 4000, 4004, and then came Intel 8088, and then from here on we move on up till to like 2020, where the size is reduced to nanometers from thousands of nanometers to just maybe 1 or like just single digit nanometer. The size of the processor is reduced. So transistors have been in use since the 1940s actually, and in different machines, but the digital machines started using transistor in the late 1950s, and hence then the computer generation began and were commercially available. So in a basic computer, the circuit chip, that is the processor that we see, has basic modules, and these basic modules include the logic gates. Now, these logic gates are made up. Yes. So these logic gates are made up of billions and billions of switches. These are like transistors, which passes or stops the flow of electricity to store the data. These transistors are made up of silicon, and which is the second most abundant material found on Earth. So, like from 1950 to 2020, 21, like these transistors have evolved, as we can see in this particular picture, and along with that, evolved the computers also. So, from 10,000 nanometers to 7 nanometers, or like 3 to 4 nanometers, the size of the transistors kept on decreasing, and it's still decreasing. Like basic transistor used in the processor is of like around 40 nanometers, which is like 14 times wider than a DNA molecule in a body. So decreasing its size more will lead to the size of a single atom. In that case, transistors can't act as a switch. So now here comes a question that what should we do now, or what is the future of the particular transistors? So here comes the future of computing. Now, how we decide the future of computing? So from classical computers to supercomputers to optical or like photonic computers to like quantum computers, computing technology has evolved a lot. Now, the size of processors is decreasing, as we already saw, which leads to more efficiency, of course, speed and less power consumption. But at the same time, it is very difficult to manufacture this kind of processors like in this kind of size. So the size of since the size is getting smaller, it's getting close to the size of a single atom, in which case the electrons can be stopped for use. Now, this phenomenon in which the electrons move through the transistors without stopping, it is known as quantum tunneling. So here, the electrons are stopped as per need, and they can be used at that particular thing. Now, it happens when the size of the transistor is equal to the size of the atom. So if we keep on reducing or like decreasing the size of the transistors or the processors, there will be a point where the size of the transistor will be the same as size of an atom, and then the quantum tunneling effect will take part. So when it happens, quantum computers, like normal computers cannot work efficiently. So here comes the quantum computers or like optical computers. So like mostly the research projects, like they are focusing on replacing current like classical computers with like optical equivalents, of course. This approach appears to offer the best short-term prospects for commercial optical computing. For this, electronic transistors are replaced with optical transistors, of course. Now, in case of a quantum computers, they are believed to be able to quickly solve certain problems that no classical computer could solve in a feasible amount of time. So unlike the classical computers that we are using, suppose the laptop from which I am presenting, it is a classical computer. But if I were to use a quantum laptop or maybe another kind of laptop which uses quantum technology or maybe optical technology, then it will be more feasible, it will be more faster than the normal classical computers. So it is now this point where the classical computers dominate the quantum computers or the other computers dominate the classical computers. This is known as a quantum supremacy. Now, before moving on to the quantum computer, first we have to understand the classical bits as well as the quantum bits. So we can see that the classical computer uses bits, which is 0, which can be termed as off or a low value, or 1, which is known as on or a high value to represent information logically. Now, byte is the unit of information storage. So 1 byte is around equals to 8 bits. So 1 byte is enough to hold one typed character, like maybe a letter like B, or maybe X, or maybe a dollar sign, like etc. So it can hold only one character, which can be a letter or anything else. So all the storage is measured in bytes, despite being very different hardware. Now, classical bits have only two states, on or off, which can be a 0, 1, or like 1 or 0, it doesn't matter. Now, both of these are mutually exclusive. So in classical bits, 0 represents low charge and 1 represents a high charge. The combination of bits is, of course, limited in classical computers. So the quantum equivalent of a classical bit is called qubit. So instead of calling it as quantum bits, we term it as qubit. So which is a two-state quantum mechanical object used in quantum computing. Now, the combination of qubits is unlimited because there is no limit to like how many combinations we can make using the qubits. So qubits can't be defined until the value is measured. Qubit has two states, 0 and 1. And there is another third state that I already told, which represents 0 or 1 at the same time. That is now how we measure it. We measure it using this formula, that 2 to the power n is equals to 1 qubit. So qubits have two states. We can see qubits have two states. So yeah, qubits have two states, and using these two states, they show superposition of both states and quantum entanglement together. Now, to attain or like measure this quantum proximity, qubits are kept at a low temperatures, like around 0 degrees Kelvin, or like with magnetic fields and all, just so as to make sure that the efficiency of the qubit or that quantum circuit is proficient, and it keeps on running efficiently. In a pure qubit state, where we can see this equation over here. So in this equation, so here we can see A and B are like complex variables, such that it gives now we got to know the both of the difference between classical and quantum bits. So now we'll be moving on with how the quantum circuits are developed. So the qubits form quantum gates. So these qubits, they form quantum gates. So in qubits, there are unlimited like ways in which they can present themselves. There are no limitations. So there can be like unlimited like ways. I think someone has raised a hand. Yeah, Kiran sir, can you hear me? Hello. Hello. Can anyone hear me? Hello, am I audible?
It's audible, sir.
Yeah, I think like a lot of participants are raising their hands. So like are like do they have any questions or something? Like if they have questions, then I can answer them, or else I'll be answering all the questions at the end. All right. So I'll move on. Now we'll see quantum circuits and how it works. So the qubits, as I told, the qubits form the quantum gates, and these quantum gates together form quantum circuits. Now, memory consisting of n bits of information has two n possible states. So just like I showed here, so 2n is one qubit. So when we form the circuit, when we want to form the circuit, so there are like 2n possible states. So we can begin by considering a simple memory consisting of only one bit. Now, this is a picture of uh, quantum circuit, but this is just a concept where it's not properly described how the quantum circuit will look like. But of course, we can see the quantum circuit. Like there are a lot of pictures available. There are a lot of research work is available going on. So we can easily see the picture of a quantum circuit, maybe just a reference picture of the quantum circuit in the internet. Now, quantum memory may be found in any quantum superposition of the two classical states, that is 0 and 1. Now, there are a lot of equations are there are a lot of things, there are a lot of mathematical like no lot of numerical problems are there, and we have to solve all of these problems in order to get like complex numbers, where like these numbers will be representing quantum amplitudes, and like apart from that, there are a lot of other equations. Like we have to solve a lot of equations in order to move on and get the perfect or like that efficient quantum circuits, which will be which can be used for quantum computers. Now, most quantum circuits depict a network consisting of quantum logic gates and no measurements. So this is all about the quantum circuit. Now we'll move on with the quantum computers and how they work. So as we know that qubit is the main building block of quantum computation. So quantum computing is the use of quantum phenomenon like superposition and entanglement for computation. Now, quantum superposition states that any two or more quantum states can be added together, and the result will be another valid quantum state. So when we have two or more quantum states and they when they are added, so it can be the result can be valid, like it will be another valid quantum state. So quantum entanglement states that the quantum state of any two or group of particles separated by a large distance cannot be described independently of the state of the other. So quantum physics describes the behavior of electrons, protons, neutrons, etc. And all of these works on quantum mechanics, which helps in quantum computing. So quantum computer uses something called as fluid quantum reality. So this is what is the fluid quantum reality. And it also uses quantum computer also uses quantum tunneling, where we saw like where we I already discussed that the electrons are stopped and they can be used as per our needs. So computers came all the way down from classical computers to supercomputers to optical computers to molecular computers to atomic and like quantum computers. There are a lot of different computers available, and they are used as per their needs. So in the future, we'll not need any more silicon chips. So computers will be running on atoms, not on silicon chips. So this is one quantum computer where it is being tested out. So, and this one is another quantum computer which is also tested. So if you see, these are the electronics and all the components that are needed, all the circuitry is here. So temperatures. Now, this is another picture of this another quantum computer where it is being used by the researchers to see the capacity of the qubits, the circuits, and all of that. Now we have to understand the difference between a classical and a quantum computer in order to move on. So the main difference between classical quantum computer is bit that you already know. Classical computers run on bits, whereas quantum computers run on qubits. Now, classical computers use linear computation for processing, so it's slow but could process few tasks for a longer period of time, which means classical computers can only process one task at a time. Then when we want to process another task, it will be in the line. So when the first task is completed, then the next task will be processed. So it is like that. But in case of a quantum computer, it uses parallel computation. So it's fast and good at multitasking, but could process multiple tasks only for a short period of time because it takes a lot of energy and power to run a quantum computer, because it's not that energy efficient as of now. So it takes a lot of energy to compute a lot of data, or maybe just a small amount of data. So as we might know that Fugaku is the world's fastest supercomputer, while IBM Summit is the world's second fastest supercomputer till date. There is another one that is Sycamore, which is the world's fastest quantum computer developed by Google till date. So Sycamore is the world's fastest quantum computer that is developed by Google. Since 1950s to 2021, there had been massive developments in the computation technologies. We evolved from classical computers to quantum computers. But quantum computers can't replace the classical or the supercomputers as of now, because they are still in the developmental phase and there are a lot of things that needs to be done before maybe releasing them or maybe using them commercially or like publicly. Yeah, now we have to understand how the quantum internet will work. So quantum internet is sending quantum signals back and forth using photons through fiber optic cables. Right now we have a lot of fiber optic cables attached everywhere. So the internet that we are getting maybe through a broadband or maybe anything, that is like always, most of the time it uses a fiber optic cable because it is fast, it is reliable, and there will be no distortions in the signal or the speed. It is almost stable. So these photons, like the photons that will be used for the quantum, for sending the quantum signals, these will represent 0 or 1, and 0 and 1 at the same time. So there are three, as I already told you, there are 3 bits. So quantum internet is great for encryption because quantum entanglement is used for more security, which makes the transfer of data faster than the speed of light, because it is using an optic cable. So it will be more faster than the normal cables that we used for maybe transferring of data and all. Now, quantum internet will be securing quantum protocols, sending entangled information across campuses or cities, expanding the networks between states and across the whole country. This is a blueprint of the quantum internet, which is developed by the USA's Department of Energy. So here we can see these are the end nodes. There are 4 end nodes where it will be like we will get the information and all. These 2 are the quantum repeaters, and this is the switch. So all of this is connected to a quantum internet. So this is just a blueprint of the quantum internet developed by the USA's Department of Energy. Now we will see what are photonic quantum computers. So in classical computers, data transfer and data computation are done with the help of electricity, where like more processors are used for more processing power. In case of photonic computing, data transfer and data computation are done with the help of light from visible spectrum, which is like around 350 nanometers to 700 nanometers. While where parallel computing is used for more processing power. But a question may arise, why only photonics? So like breakthrough advances in photonic chip fabrication, optical telecommunication technology, and architecture scaling is the reason why photonics are like trending right now. Photonic is trending right now, and photonics are used a lot right now. Then we'll see what is Gaussian boson sampling. Now, I don't know like how many people know about Gaussian boson sampling. So here what happens, a light source is sent through an integrated photonic chip, and then it is detected by photonic number detectors and sent for further post-processing. So Gaussian boson sampling, which is known as shortly as GBS. So GBS could solve dense subgraph, maximum click, point process, graph similarities, vibronic spectra, and quantum enhanced feature. So it has all of them. So here we can see these are the single photon detectors, and these are the light sources. So the light sources are sent from here, and they go like pass through these optical processes, and they are received by these photon detectors. And at the same time, they again sent back and forth. So this is how the system is going to work. So this is a schematic diagram of the GBS. Now we'll see what is like, or like why photonic encoding is required. So qubits from an input quantum state to an output quantum state are used to transfer data, since it follows quantum laws. So photons have number of degrees of freedom. So they can easily be manipulated with high precision at about like around 99.9% of level. And since photons have no charge at all, they are the fastest information carriers till date. So the suppose we take example of RAMs. So like the RAMs we are using, maybe like the optical RAMs, they are like 10 times faster than the SRAMs and 1,000 times faster than the DRAMs, and it uses less like power consumption, like around 50%, like the from the ones that we are using. So in like if we replace the SRAMs and DRAMs that we are using with optical RAMs, so it will be more faster. And scientists can now switch between electrons and photons in a single transistor. So like the silicon photonics can transfer like data at around 1.2 Tbps, up or up to 100 meters, and around 200 Gbps for like around up to a distance of 50 kilometers. So like the fiber internet will use photonic wirings for photonic computing. Now, these are some universal photonic photonic quantum computers that we are using. So first we'll learn what is the universal photonic quantum computers, then we'll see some of the examples. So quantum computers, like as we already know, it uses quantum mechanics like superposition and entanglement. So all the qubits are connected to each other. The time up to which information lasts in a qubit is called coherence time. So like the amount of time in where like each qubit will be holding a particular information, it is known as coherence time. And controlling the qubits and the right architecture is the main difficulty in a quantum computer. So that's why it's still in the developmental phase, and like around it will take a lot of time to develop a perfect quantum computer. Like you can see some examples like companies like Rigetti, IBM, Google are they are investing in quantum chips, which are superconducting chips. So basically the silicon chips will be kept at a very low temperature so that electrical and electronic resistance is like almost zero. So they will be really fast than the ones that we are using right now. And there are like other companies like Amazon, Microsoft, Rigetti, D-Wave, Google, IBM, Xanadu, like also they are also working on the same architecture uh, and all. Now, performance numbers are not good enough to build a fully functional and operation photonic quantum computer. So, as I told, these companies are still working on it. And today, the quantum computers are where classical computers used to be at the beginning years back. This is a picture of a quantum processor where you can see the size of the processor is very small. And inside that, there are integrated electronics and all of that. All the components are also integrated. So, which makes the size even smaller. Now, this is a picture of how the Gaussian sampling is going to work. So these are like photon detectors. These are the ultra low photonic circuit, and where it has around 20 input single photons, which comes from here and it processes, and these photonic detectors detect them. So these are the pocket cells. These are the mirrors which will reflect the light or the information towards that or the photons. These works like the demultiplexers, and this is a single photon device where it is from here it is actually delivered. Now there are a lot of hype about quantum computers, right? There are a lot of hype about quantum computers, and we have to understand how quantum computers work in before we can uh, start doing or learning, or maybe start learning quantum programming, or maybe building quantum circuits, or maybe learning how the logics work, how the bits are different from the normal classical bits and all. So we have to also burst some of the myths and all that are like around quantum computers and all. Now, these are some of the applications where quantum computers can be used. Like they can be various applications of photonic quantum computers, like weather explorations, traffic monitoring systems, space communication, manuscript decrypting, quantum encryption, drug development, teleportation of information, bioinformatics, aerodynamics, signal processing, financial analysis, medical analysis, medical analysis, and defense, oil and energy, banking, chemistry, logistics, machine learning. Like there are a lot of things. Now let's see the advantages and disadvantages of a photonic quantum computer. So advantages are like they are accessible, they are scalable, versatile, and resource efficient. At the same time, photonic quantum computers are modular and customizable. Photonic quantum computers are well suited for distributed quantum computing. They are friendly to environment, and the like unparalleled robustness is there against the noise that will be there. There's a highest possible like clock rates are there, arbitrary connectivity is there, and no cryogenics and vacuum systems are there. So that these are the advantages of photonic quantum computers. Now let's see some of the disadvantages of them. Like we have to use a default photon source, like they are like most probabilistic. So entanglement operations are also probabilistic. So there, like sometimes there are a lot of photon loss, which creates a loss of the data or information. Right now, they are costly to develop and build and manufacture. So maybe in a couple of years, or maybe in the near future, they will be very cheap of like the classical computers that we use, and we'll be able to buy them from the market or somewhere. And like the materials that will be using, they are also not available as of now. So we are still figuring out to develop how to use different materials in case of that. Now, with that, I'd like to come to the conclusion of this topic, where I discussed that the photonic quantum computers, they are not similar to the one that we use right now. So computers were from around 1950s or before that. Until date, they are still there. And since then, there have been many fixes like developments, innovations, technological advancements, or the evolutions we saw. We saw a lot of generations of computers. So as technology will grow, the need for more power and speed will undoubtedly grow along with it. The principal concern of quantum computer comes from the fact that it involves the use of qubits. So photonic quantum computers are being developed as of now because it uses photons. So we are still not yet of developing qubits and all of that. We are still doing research. So right now we'll be using photons instead of qubits to like do all of that. So clearly the future of computing lies in quantum computing or in photonic quantum computer, whatever will be there. But it shows a lot of potential for future uses. With further research and experiments, so quantum computers could be used anywhere or everywhere, and the world will need like we'll see that there will be a lot of connected qubits, and they will be tackling some of the useful problems in our society and around this globe. And this is why there's like so much interest, and even though it's so far down the road for everyone to achieve the perfect quantum computer, but even for this they are doing like the companies are doing a lot of research, because they know that today they are using the classical computers, but in future they will be using that. So this is all about quantum computers. And so with that note, I'd like to give a thank you to all of you for patiently listening to me and all. So if anyone is having any questions or anything, I'm open to all. Hello, am I audible?
Yes, sir, you're audible.
Yeah. So yeah, so this